this. So we want to identify some graphs. For the next few lessons, Thomas, we're going to be looking at different graphs because our eyes are good at spotting visual patterns. At the same time, drawing graphs is a pain. And so after we've mastered graphs, we're going to say, okay, now that I've wrapped my brain around what's going on, isn't there a way I can do this in 2 lines with equations instead of in a page and a half with a graph? And the answer, Gurjo, will be yes. But we'll start off visually first. And so here's what we're going to do. I have a graph for you right here. It says this: indicate which graph matches the statement. And the first statement is, a train pulls into a station and lets off its passengers. A train pulls into a station and lets off its passengers. And the graph that we are graphing, on the y-axis we have speed, and on the x-axis we have time elapsed. Speed versus time elapsed. There is 1, 2, 3, 4 different possible graphs. I'm going to tell you that one of them is probably the best answer if you were graphing what a train would look like if you were graphing speed versus time as the train pulled into its station and let off its passengers. So we have graph A, graph B, graph C, and graph D, and I'm going to ask you to vote which one you think is best. So first of all, without voting, without thinking, without saying anything out loud, I just want you to think about it to yourself. Taylor, you with me? Put that away. Whatever you're looking at, focus here. It's called an attention span. Thank you, my friend. You ready? Who says, Mr. Dewitt, graph A? I think graph A is the best graph. Graph A. Mr. Dewitt, graph A. No one. Okay. Graph B, Mr. Dewitt. I think it's graph B. Ooh, lots and lots and lots. I'm just going to write lots. Graph C, Mr. Dewitt. Graph C. I think it's graph C. Graph C. No one. Graph D? 1, 2, 2. And so, as we always do, you'll be voting a lot during the year. I'm going to force you to have an opinion. Then I always say you can convince me by either attacking someone else's answer as having to be wrong or defending your own answer as having to be right. Convince me. Jenna, which one did you vote for, or are you attacking another answer? I find either way.
I was attacking another answer.
Which one? Okay, you're going to attack which letter? Why must D be wrong? Train is going at a constant speed, instant stop. By the way, that would be a graph of a head-on collision. That would be bad. Now, can I give you some context? In Math 10, you learned something called the vertical line test for functions. You learned, and this is what drives me crazy about the way they teach math, they teach everything so much out of context. You learn, and your teacher probably used like a little meter stick, or their finger, or a pencil, you learn that if you run a vertical line along a graph, and if it touches the graph in more than one location, right there at the same time, they tell you the graph is not a function. And all of you learned that for the provincial exam, and you dutifully memorized that, and you, okay, fine. Garbage. Yeah, that's true. That's true. And that is, Linnea, hugely important when you get to calculus. But you know what? In physics, if a graph fails the vertical line test, it's impossible or you're dying. Like, it's bad, which is to me a much better explanation of the vertical line test. Here, not only is this an instantaneous change in speed, but here's what it's really saying. At the same time, you're going this fast and 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 this fast. The only way you can be going at multiple speeds at the same time is if something's gone horribly wrong. You have to be in pieces, right? I mean, that's the only way I can think of that you can be going several different speeds at once. So those of you that voted D, okay, that's a car crash. What's wrong with A? Yeah. Yeah. This would be jump, I guess. Probably not the best way to deliver passengers. What's wrong with C? Okay, what could C be a graph of? Yeah, this is those of you that are getting your licenses, once you drive in rush hour, you'll discover this joy for yourself. Red light, the light goes green, and I'm like the second car, so I get to go a little bit, but then I catch up to the traffic, past the red, I hit the brakes. But then traffic slowly starts to move, I hit the brakes, and it kind of levels, and eventually, if you're lucky, traffic moves at a constant speed. During rush hour, it's actually probably a little lower and not quite as good. You with me? Have I convinced you? Okay, second one, next one. Ready? A man takes a ride on a Ferris wheel. And on the y-axis, we're going to graph distance from the ground, height. On the x-axis, we have time elapsed. Okay? Ferris wheel is the ride at an amusement park that goes in a great big vertical circle. Okay? So, A, B, C, or D. We're graphing height versus time elapsed. A, Mr. Dewick. A, that looks like a ferret. Ferris wheel goes A. Mr. A. No one. B, Mr. Dewick. I'm like in B. 1, 2, 3, 4. Jenna, is that a vote? Because that could have been a hair. That might have been a very smooth. I'm not. Are you voting or no? Okay. Hands, sorry. Keep the hands, sorry. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, blah, 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 blah. Okay. I could have just subtracted hands down, I guess. C. That wasn't a vote up? Okay. Sorry, I'm always looking for the little twist, right? D. 1, 2. Once again, you can attack or defend. Convince me. Luke, which one? What are you defending or attacking?
I'm attacking D because he can't go back in time.
Ooh. Do you see what he's saying? In D, suddenly you magically go back in time. I would have an issue with that. Also, in D, let's suppose we look at this time right here. At the same time, you're that high and that high and that high. The only way that can happen is if your body is in different pieces. That's bad. Also, does D pass the vertical line test? See, in physics, if it doesn't pass the vertical line test, you want to be a little nervous of that graph. I can't guarantee that every physics graph will pass the vertical line test. There are some very obscure ones want circles and ellipses and things that, but no. Oh, and for the same reason, no. So you guys figure B, I agree. Have I convinced the two of you that voted for D why it can't be? Good. Is there an amusement park ride that could look like C? Oh, let's see. You get on the roller coaster and it starts out at ground level, takes you up the first hill. You don't go quite back to ground level, and because you're losing energy, you don't go as high up the next hill. You don't go as high up the... Sure, roller coaster would work. I'll go with that. I'll go with that. Okay. Number 3. A woman climbs up a hill at a steady pace and then starts to run down one side. A woman climbs up a hill at a steady pace and then starts to run down one side. And we are graphing speed versus time elapsed. A. Who says A? I'm going with A. Ooh, only a few. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Ooh, a little controversy here. B, Mr. Dewick. B, that looks like a hill. No one. I'm liking C, Mr. Dewick. I'm liking C. Really, I think D. Got to be D, Mr. Dewick. Really? I got 13 cowards in this? I got 13 people with courage and the rest of you are wimping out on me? I'm not accepting that. Not accepting that. We're going to start over. You have to vote. Who says A? I'm going with A. Oh, now peer pressure kicks in. I don't want to have an opinion. I'm going to vote with my friends. Oh, teenagers, I'm embarrassed. Convince me. Linnea.
You said you want a steady
Okay, so what would a steady pace look like on a speed versus time graph? All lines are straight, Captain Obvious. Horizontal. Oh, okay. So a constant speed would be a horizontal line, steady pace. Now, eventually, she'll max out her speed on the hill. If I wanted to continue this graph, I think it would probably also end up at a higher constant speed. And all of you learn this when you're 5 or 6 years old, when you try running down a hill and it goes horribly wrong and you take your gravel tumble. Probably you would also end up doing that shortly because she'd wipe out. She'd bail. Yes? What could this be a graph of? C. So when you walk uphill, you speed up? I'm going to disagree with you there. I mean, you can. Hey, I'm a fitness freak. I'm a triathlete. I'm going to sprint up. But even then, I think you'd hit a constant speed pretty quick. Haley. Okay. Patrick. Those of you that are getting your driver's license, I think that's not a bad graph of merging on the freeway. You floor it, or you give it some acceleration, yes, but then you very quickly settle down to whatever the freeway speed is. Now, I don't think it'd be jagged here. I think it'd be kind of curvy, a little smoother, but I think the shape is right. Okay. Let's go back to your childhood. A child swings on a swing set. Oh, fun days. And we're going to graph distance from the ground, height, versus time elapsed. Which of those would be the best graph of height versus time? A, Mr. Dewick, A. B. Is that a vote, Lyndon, or that? Oh, okay, sorry. Because that could have been, I'm not sure. C. D. Who didn't vote? A, B, C, or D? D? Which one are you going with? D? Okay. Daniela's, what have I gotten into? I do things a little differently, sorry. Dear Diary, Mr. Yeah, keep me out. Yeah.
Can't be D.
Why can't it be D?
It doesn't go close to the ground.
My issue with D is, on the first swing, you're that high off the ground. On the second swing, you're that. I think you hit the same height at the bottom on a swing every time. Do you not?
Yeah.
So I would argue I don't think D can be right. Why is A right? What's happening right there?
You're at the lowest.
Okay, so, and you're getting to the lowest point all the time, yes?
Yeah.
Why are the heights increasing? You figure this out when you're 4 or 5 or 6 years old. I don't know, do kids do this? Is it instinctive? But every one of you shared learning experience is, you know how to make a swing go higher on your own. Now, usually you call it pumping. In physics, we say you're adding energy to the system. You're taking energy from your muscles and you're adding it to the system, and that's why you're going higher. It's also why eventually you'll get tired. What could graph C be a graph of? I thought sort of bungee jumping, except when you bungee jump, you don't get back to the same height you started from. If you did, there'd be real issues, right? You'd schmuck against the bridge, which wouldn't be good. So if it ended like right there, or if you stood on a platform like in a hayloft with a rope swing and you jumped from the rope swing and took a big swing, but again, you don't get back to the same height. You're always losing some energy. We'll talk about that later on this year when I introduce you the law of conservation of energy, which dominates your life. It explains an awful lot of stuff. Haley. Hold that. What could D be a graph of? Haley. Maybe, here's what I thought. Imagine you had like a picnic table next to the trampoline, and the picnic table was slightly higher than the trampoline. And now some of you are saying, Mr. Duick, why don't you just say you're jumping from your sun deck onto a trampoline, because that's dangerous. Don't do that. Okay? You land, and on your first bounce, you go, because you've started from a certain height, furthest down. And if you don't add energy, if you don't bend your knees and add energy, you'll get your highest bounce, then a little less, then a little less. That might work. Or somebody else suggested someone who sucks at a pogo stick. They jump onto it, they get their first big bounce, and they're falling, and they wipe out. And each successive bounce, because they're going off balance, they're not going as low or as high. Okay. Last one. A child climbs up a slide and then slides down. And we're going to graph speed versus time. A child climbs up a slide and then slides down. A, Mr. Duick. A. That looks like A. A. No way. B, Mr. Duick. I'm going with B. I'm telling you B. B for back row. We got two of them. C. Ooh, lots. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. Thomas, you're not Donald Trump. You can't change votes that easy. D. 1, 2, 3. Thomas, you want to change your vote?
Yeah.
What did you vote initially?
I voted
I don't think so, because A to it, and I can count. I think you voted B initially, because I remember these things.
Yeah.
Boy, this is the Trump election. You're rigging the vote already. What do you want to move it to? Darcy, you have something on your mind?
Yeah, I'd like to change my vote as well.
From what to what?
From B to C.
Why must B be wrong? Why is it impossible? Yeah,
Increase in speed.
not just that.
And
It's failing the vertical line test on those little sections. See, that's my trigger. As soon as I see that, I'm going to be really skeptical. You really have to convince me that it's doable. There are some out there that can't, but for the most part, I don't think so. All right. Talk to me. What's going on this section right here? What is that? What's happening for that little horizontal line? All lines are straight. What's happening? Huh? More specific, though, on the playground, what's the kid doing? Walking or climbing up the stairs at a constant speed, walking to the slide. Okay, what's happening for that section right there? Why does the speed drop to 0? And when you're 6 years old, that's a long way down. You're sitting there, you've got to psych yourself up. Here we go, here we go, here we go. It's happening right there. So your speed increases. By the way, if this was a velocity graph, since down is negative, we would have had it actually going like that. That's why I was careful. I said speed. I wanted the scalar value. What's happening right here? Well, what's your final speed when you hit the ground? After you hit the ground? Yeah, ground brings them to a stop. Okay. It's a beautiful sunny day. July. Not a cloud in the sky, and you're at the playground. And the slide is empty. You walk to the playground slide. You climb the ladder. You sit down on the sheet metal slide, and you realize why the slide is empty on this frying hot summer day. The sheet metal slide is like 150 degrees, and it burns your legs because you're wearing shorts. And rather than slide on the slide, you roll over and fall straight down to the ground. You roll off the slide. What would that graph look like, speed versus time? Mr. Duick, you said speed. Isn't that velocity? No, that would be velocity, right? That's speed. Okay, let's see. I walk to the ladder, climb the ladder. I sit down. Fire! Bah! Aye! Ah! And I roll off. What happens to my speed? What about when I hit the ground? Mr. Dewick, are you saying it has the same shape as the original slide graph? The physics of those is the same. The would be different, but the physics of what's going on is identical. The speed changes are happening for the same situations. It's a beautiful summer day. You're at the playground, and the slide is empty. But Simmy, you've got a little rebellious streak in you. Only losers use ladders. You're going to go up the slide the other way. Come on, you've all tried this at least once in your life. You're going to go sprinting towards the slide itself. You're going to go sprinting up the slide, feet slipping, feet slipping. You're going to dive forward and get your hand in that crack at the top of the slide, because it seems like every slide has a little crack right there. Pull yourself up, gather your breath, and then climb down the ladder. What would that graph look like, speed versus time? Patrick.
You have like speed going up when you're like gaining speed.
So first of all, let's go sprinting towards the slide. Let's suppose you've hit top speed. You hit the slide. Now what?
Start slowing down because you're going up.
Come to a stop for a split second when you kind of pull yourself and change direction. Yep.
And then go up a little bit more because you're moving up. Then you stop. And
Climb down the ladder. And when you get to the ground, what's your... Mr. Dewick, are you telling me that that has the same shape as our original graph too? Yeah, because in terms of the physics that's going on is the same. The values, the heights would be different, but I'm telling you, same shape. You can learn an awful lot from the shape of a graph. You have to, first of all, always make sure you know what we're graphing. Look at the y-axis, look at the x-axis. But what I tried to tell you a couple of weeks ago is, in physics, slopes, heights, x-intercepts and y-intercepts mean something. They're not just numbers that you're supposed to find with an x and a y. They mean something. And on that note, let's move on to lesson 2. Lesson 2 is going to seem... It's because I couldn't shrink it down, because I stole a lot of the graphics from the internet, and when I shrank them down, you couldn't read the numbers on the graph, which kind of defeated the purpose of the graphs. So it's like 15 pages. It's huge. Patience. We're going to go right to the tone. You're not going to get any homework today. We're going to finish the lesson off on Tuesday. Tackle it from there. The first activity says identifying qualitative graphs. We just did that. So now we're going to actually start looking at some actual data. A person walking along a straight line is being timed while their position from the starting point is recorded. The data is recorded in the following table. You can freehand this line, or you can use your calculator to draw the straight line. I'm not going to hand out the rulers. I'm not going to be that fussy. But it says graph the data below. Let's at least do our proper procedures. We said every graph has to have a title. How about distance versus time? We, when in doubt, put time on the x-axis. We said you needed to label the axes. So my y-axis is going to get labeled with distance, comma, d in meters. My x-axis gets labeled with time, comma, t in seconds. Right? Then we pick a scale. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. I got 22 squares horizontally. In the time chart, what's the biggest value that appears? 9. So I need to fit 9 objects in 22 squares. What would be a good scale? How about every 2 squares is worth 1? Yeah, go up by halves, but I'm not going to label it that way. I'm going to go like this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Vertically, I have 2, 4, 6, 8, 10, 12. I got 14 squares to work with. Y value that shows up. Huh? 20? And I got 14 squares, so I can't go 1 for 1. You know what? I guess I'll let each square be worth 2. Except I'm going to label every other square. So I'm going to go like this. 0, 2, 4, 6, 8. 8, Mr. Dewick. 8, Mr. Dewick. 10, 12, 14, 16, 18, 20, 22, 24. I'll put a 0 here too. Someone in my last class said go up by 3s, and I could. Just 3s are yucky to do math with. I try and avoid them unless it's really necessary. Go up by 2s, 4s, and 5s, and 10s. Okay? And now we graph. What's the first point? What, comma, what? 1, comma, 4. What's the next point? 2, comma?
6.
Is the next one 3, comma, 8? Because I've spotted the pattern. And then probably 4, comma, 10, 5, comma, 12, 6, comma, 14, 7, comma, 16, I'll bet you, 8, comma, 18, 9, comma, 20. By the way, the fact that this graph works out perfectly tells you I faked the data. I made it up. Usually, if you're measuring data, there's what we call noise. Some of the points won't quite line up, but they'll be close. It's one of the ways that we look at research papers and determine whether they're frauds or not. We look at their data, and it's amazing how often when you run the data through an algorithm, you can show, now this data's fake. There's no way you're getting that accurate. By the way, what would the y-intercept be? Does this graph go through 0, 0? In fact, I think it goes through exactly right there. Yes? If you have something to draw a straight line with, a straight edge, try and do that. Otherwise, just this once, I'll let you freehand it, but we'll draw our line of best fit. Is that okay? All right. Part A asks, what's the y-intercept of this graph? A lot of you are way overcomplicating this. The y-intercept is right where it crosses the y-axis, and you just read it. In this case, the y-intercept is that right there, which is what, comma, what? 0, comma 1? What's each square worth? And again, don't get into the habit of counting squares. Look at your axes. This is why a lot of you on the test got the slope wrong, because when you graphed it, it was 1 square by 1 square, so you said, oh, that's a slope of 1. Each square wasn't worth 1, though. So Taylor, what's the y-intercept? As a number, 0, comma 3, 2, I think, yes. Sorry. What's the y-intercept here as a concept? This person got a 2-meter head start. Yes? Because where do most people start a race at? 0. And I'm telling, again, what I'm trying to get to you to start to think about, Patrick, is what do y-intercepts, what do x-intercepts, what do they actually mean? They tell me something now. What's the slope of this graph as a number? Taylor, you might be tempted to say the slope is up 1 over 2. The slope is 1/2. Don't count squares. This is why, now, by the way, this is a nice, perfect graph. If this was real data, I'd try and pick points that were nice and far apart to kind of eliminate the noise as much as possible. Here, I'm going to keep it simple. I'm going to use this point and this point. Reading here, how high am I? 4. How high am I? 2. What's the rise? 2. Over 1, 0, 1. Now that's the slope as a number, and in your head, 2 over 1 is just plain old 2. But what does the slope mean? You ready? What are the units on the y-axis? You can read this. Meters? That's the rise. What are the units on the x-axis? Hey, what's meters per second a measure of? This is why I told you a couple of days ago, it's really worth memorizing what units go with what concepts, because you can actually figure out what a graph is telling you without memorizing all the 80 graphs that are out there. Last year in Science 10, some of you probably were dumb enough to memorize the slope of a distance time graph. What is the slope telling you? What is meters per second? Speed or velocity, in this case speed. Some of you probably memorized that last year in Science 10. That's a waste of brain power. If you already know that slope is rise over run, look at the units. Hey! The slope is speed, or if it was a displacement versus time graph, velocity. How fast is this person traveling? 2 meters per second. That tells me something. What's the equation? So all equations are based on y mx plus b. Sorry, all linear equations are based on y equals mx plus b. Curves aren't. But I've tried to tell you, get away from using the stupid y. Thomas, you with me? You're not foolishly on your phone or anything right now, are you? No, because if you were, I would have taken your phone away from you. Your phone's in your pocket, out of reach, right?
Right.
Put it away. I'm not going to use a y. What would be a much smarter letter to use here? How about something for distance that matches the variable that we even used in the equation the other day? D, you say. Well, that would be clever. D equals, what am I going to put in for m, the slope? What is the slope this time as a number? I'm not going to use x. What am I going to say instead? Plus, the y-intercept also happens to be 2. Mr. Duick, are the slope and the y-intercept always the same? That's just a fluke. Don't memorize that. It just so happened. Let's try and generalize. Next page. Josh, can you read to me the first 2 words on the next page?
The idea of the
You know what? If it says key idea, you probably want to put a star next to it, or underline it, or draw a box around it, or highlight it, or something. What's the key idea? The slope of a displacement versus time graph is, what do I measure displacement in? First of all, what do I measure displacement in? Meters per. What do I measure time in? So without even memorizing, can you derive what the slope of a displacement versus time graph must be? It's meters per second. It's either speed or velocity. Displacement, vector or scalar.
vector.
So I'm going to say velocity. If it was a distance versus time graph, speed. So let's look at an actual graph. These are graphs that are just sketches. I'm not going to worry about putting a title or an axis or labeling. I just want to see if I can spot the shape. So it says, what can we say about the motion of the object graph below? First thing I always check is, what kind of a graph is it? What's on the y-axis? On the y-axis? What's on the x-axis? Okay. We'll be looking at 3 graphs this unit. We'll be looking at distance versus time, velocity or speed versus time, and acceleration versus time. So get in the habit of checking which graph it is, just 'cause. So I wrote down here, time is still increasing to the right. Time's getting bigger. But the distance is, ooh, someone said a math nerd word. I almost forgive you for the phone. Not yet, but almost. What was that? Loud and proud? Because on this graph, your height is your distance. And although time is moving forwards, the height is not changing. So here's the question. If your distance isn't changing, but time is still moving, but your distance isn't changing, how fast are you traveling? I'm going to ask you the same question. I'm just going to phrase it differently. What's the slope of the line there? 0. In math, they tell you that a horizontal line has a slope of 0. In physics, I'm telling you it has to be, because if you're not going anywhere, your speed's 0. Okay? We have a fancy physics phrase. When an object is stopped, has a velocity of 0, we say that it is at rest. That's the phrase that I will use most often. Next unit, we'll ditch the graphs. We'll go to entirely word problems. And whenever you see the phrase at rest, you'll underline it, because that tells you that the speed is 0, which makes the math nice, because it usually means you're doing math with the 0 times table. And even Patrick can do the 0 times table. Patrick, what's 0 times 5 in your head?
0.
What's 0 times 10 in your head?
0.
What's 0 times pi in your head?
0.
What's 0 times a million in your head?
0.
See, if Patrick can do it, I figure all you guys can too. All right. What can we say about the motion of the object graph below? What are we graphing? Distance versus time. Oh, they've added something else. As your height increases, apparently that is north. Okay. So, A, what direction is this object traveling? North. That's right. You're right. What would it look like if it was traveling south?
Move down.
Oh, okay. So here's the question. What does a line with a positive slope tell you on a D versus T graph? In this case, north. If they don't specify a direction, let's keep it simple. This is what drove me crazy about your Science 10 textbook last year. I thought they really overcomplicated direction. Forwards. Example 2 says sketch 2, or example 4 says sketch 2 different graphs of an object traveling backwards at a constant speed. Okay, so here's a distance versus time graph. How would I show an object traveling backwards? How would I show another object traveling backwards faster than the first graph? How could I show that it was traveling faster? Because slope is velocity or speed. So steepness tells you how fast. Faster backwards. Slower backwards. Even slower backwards. Completely slow backwards. Oh, at rest. That also makes sense, actually. Yeah, you're going slower and slower and slower and slower. Stopped. Okay, should be a slope of 0. Next page. Here are 2 objects. Object A, the solid line. Object B, the dotted line. Double check what kind of a graph this is. True or false? Object A traveled further than object B. It's funny because I saw about 10 people nodding their heads for true, and I saw about 10 people shaking their heads for false. The good news is, some of you are right. Convince me. True or false? Convince me.
They stopped at the same place. A just took longer.
Stopped at the same place. No, they didn't. B stopped right here. A stopped right there. That's not the same place. I think I know what you're getting at, but I think your explanation was sloppy. Where does how far appear on this graph? Yeah. How high it is. So if they traveled the same distance, they should have ended at the same height. Did they end at the same height? Did they end at the same distance? Convince me. Same height. And height is your distance on this graph. All right, true or false? Object B had a head start on object A. Thomas. Ooh, he even used another math word. I had to coax the origin word out of my other class this morning. So, false. I like as short an explanation as possible. Same origin. You guys have already picked up. I tend to abbreviate, and if I have to write it out, I'm going to be concise. All right. C. Hey, which object was faster?
Object B.
Object B? Convince me. You can answer with one word. Can you change the phrase more steep into one word? Heck, since I did 2 words in all my other ones, I'll do steeper slope. And what was the key idea? When I say slope on a distance versus time graph, what's that a synonym for? Speed. Steeper slope, bigger speed. All right, next thought experiment. How would we draw an object that was speeding up? What's the key idea? Come on, what was the key idea? It's at the top of the couple of pages ago. Yes?
Steeper is faster.
Okay, so how would I show speeding up? The object will get steeper. Curve. Curve. Can't be a line. Now, this year in math, I think, have you guys started looking at the parabola yet in your math classes? You're starting to look at some interesting curves. This graph right here is incredibly profound. It would look something like this. Do you see the slope is increasing? Here the slope is about that steep. Here the slope is about that steep. And what's slope the same as on a distance versus time graph? Speed. The reason, Christina, the reason this graph is so profound, that right there forced Isaac Newton to invent calculus. He asked, okay, how could I find the slope of a curve as a number? Can't use rise over run. And he had to invent an entirely new branch of mathematics. Calculus deals with 2 things. And the first thing is finding slopes of curves. Second thing is finding areas underneath the curve. So he also figured out how to find areas of curvy shapes. Is that all right so far? Example 7. Connor, you awake? Good? Okay. Example 7 says, describe the motion of the object. You know what? I'm going to retype this question, but for now, do this. Put a little capital letter A right there. Put a capital letter B about halfway up the first curve. Put a capital letter C right at the top. Capital letter D right about there, and a capital letter E right about there. What we'll do is we'll describe what's going on at each letter. Because describe the motion is, to me, is too vague. So, at location A, what's going on? First of all, are we at 0, 0? Okay, so it looks like we got a head start. How far? Don't know, but we didn't start at the start line. We got a head start. And if I look at the slope right there, I think for a split second it's kind of horizontal. Yes? If I really eyeball it. So how fast did we start out at? What was the slope where we started out? Horizontal. What's the slope of a horizontal line? 0, 0. And what's slope the same as on a distance versus time graph? So, ready? How fast did we start out at? A speed of 0. Okay, pause. Ready? Again, my argument is right there. It does look horizontal, and the slope tells me the speed. So you know what? Head start, I'll use the fancy physics term, at rest. How do we get to location B on the graph? What are we doing? And you'll notice the slope is increasing. Also, you'll notice just past B, now it gets less steep. Yes? Because how fast are we traveling? How fast are we traveling right there? What's the slope right at the top for a split second? I think for a split second, isn't it that? Like right at the very, very top? How fast are you traveling if that's your slope on a distance versus time graph? So in B, we're speeding up. C, slowing, and then we stopped. Slowing, where you can see it getting less steep, less steep, less steep, less steep, less steep. By the way, look at all the information we're able to get from this shape. Lots there. D. How is D different from B? What's the big significant difference? I'm not sure it is. Remember, the magnitude of the speed is the steepness. I think it's still pretty steep there. So I think you're still going fast. Luke, what? Direction. Speeding up. Backwards. It's a long blink, Linnea. You going to make it? I said that's a long blink. You going to make it? What's happening at location E? What's the slope at location E? If you want me to describe this like completely smoothly, you start out speeding up, going forward, you start to hit the brakes, you come to a stop, you throw it into reverse, you're going backwards, 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 speeding up, and then hitting the brakes again, you end up back where you started from, hitting the brakes and stop. What would that be a graph of? If instead of forwards and backwards, if we replace forwards with up and backwards with down, and the head start would be the height off the ground. Maybe. A little more complicated than that, but close. We're going to finish this on Tuesday.